Swayam Prabha. Digital India. Educated India.
I want to do a mental experiment. So we have a turbulent flow. In this turbulent flow, I release particles. And I release the particle at some time, and I watch where it is after time t star. All the particles will, on average, will go down some distance that depends on settling velocity times t star. But since the flow is turbulent, some may go to the right, some to the left. In other words, if I repeat this experiment million times, I will have a distribution of particles. And this is dispersion. This is called turbulent dispersion. So in other words, if I release the particle repeatedly at the same spot, and this is a stationary turbulence, turbulence is the same, but it keeps changing. So in other words, the later position of the particle at any later time is a random variable. It just fluctuates. Okay. So I have my notes here and I want to follow this. So the reason this is important is that many of you probably are calculating if the volume fraction is there. Let's say you solve an equation like this. Okay. So in other words, if you have a volume fraction, this is the mass balance equation for the volume fraction. But I don't know how many of you stick in a diffusion term in here. I don't know, people are doing Euler simulation where you are solving the concentration equation. You may not call it phi, you will call it C, but you stick in this diffusion. Okay. Many times we do this for numerical stability, but you might want to think, where does it come from? It basically attempts to model this. This is particle diffusion or dispersion. It accounts for the fact that particle will disperse. Okay, and how do you get this value? And this is due to turbulence. Most of the time, you try to account for the fact that since the flow is turbulent, there is dispersion, and this dispersion is you try to account for it. So one measure, how do you measure it, is the question. So in this case, if you call big X of location of the first particle at some time t star, in location of the second particle at t star. So these are these various red dots that I have drawn here are these positions. So in other words, you are repeating this problem again and again and again, and you collect all the X positions. Now you can talk about the mean X location. That is the center of this cloud. The different values of X are all over the place. It's a random variable, but its average is going to be hopefully straight below, because some particles would have gone to the left, right, etc. So this is the mean location of the cloud. Now what we are interested in is the spread around the mean location, how far it's going to be spreading. That comes from the fact that X of every particle is different from the mean value, and you take the square. So this is the RMS. This is proportional to r square, where r is the radius of the ball. So in other words, all I am calculating is position of every particle, how far it's deviating from the mean value, square of it, and I average, and that should give you an idea about how big the ball is. Okay. And this R increases with time because it's dispersing. At very short time, this ball may be very small. As it goes down, it not only goes down and down, but it's spreading over a bigger and bigger ball. Now, if I know how this R increases with time, that should have something to do with the dispersion coefficient. The faster the ball goes, you will say it's dispersing very fast. The turbulence is lot. Okay? So this D, to get that, so when we do Euler simulation, we need this D, and the only way to, or one way to get it, is to do this kind of an experiment, and from how big the ball goes over time, you can back out, okay, oh, this must be the dispersion coefficient. So Taylor did a great example, and I want to talk about that. Okay, to model this, what I showed earlier in the previous picture, the take-home message is RMS particle position. That's what we had here. RMS, actually not RMS, mean square particle position, mean square from its central value or the mean value, gives a measure of R square value. This how big the ball's radius is. Now this is in 3D, but we want to consider this in a very simple problem. What Taylor did was, he said, okay, let's say a bug is there and the bug will move to the left or to the right. Those are the only two things it can move. And in 1 delta t, it can go minus v delta t to the left or plus v delta t to the right. So in other words, this is also sometimes called drunkard's walk. So sort of people going like this. Okay. So every time they may go to the left, they may continue to go left, or then they may change. Okay. So drunkard's walk problem, but made one dimensional. Okay. They can go right or left. Okay. And this is what we will call delta x I. So delta x I, for I equal to 1, 2, 3, etc. You can do this problem using simple computer code. You just have to randomly pick plus or minus. Okay. And then you can find out what is x, mean value of x. Well, that's going to be 0, because the drunkard has no preference. It could be left sometimes, it could be right. If you repeat the experiment with different bugs, it will average to 0. But what we are interested in mean square value. That's not going to be 0. So in other words, if you set out a bunch of bugs or tens of thousands of drunkards, where they will lie, we don't know. That's going to be a very interesting question. So what we are going to do is that, so let me also put n here. So in other words, after n sort of these motions, random motions. So we are asking, since the mean value is 0, I don't have to subtract the mean anymore, because the mean is 0. So what we are asking is, what is the mean square position of these bugs after n random steps when you do millions of these bugs and do an average? So this obviously is equal to delta x1 plus delta x2. So each time it's a plus or a minus n of them, but you square them and you do the average. Now, turbulence is not this totally random walk. If you are in an eddy, you are moving left, you are likely to continue to move left. Or if you are going to move to the right, at least for some time, there is what is called correlation time. So that's what I am going to introduce. So your motion will be correlated, but you will keep moving right or left for some time, but you catch in the next eddy and you may go the other way, and you catch the next eddy, you could go some other way. Okay, so we want to build that in. So Taylor is, of course, a brilliant guy, and he said, okay, he said delta x I and delta x I plus 1, it's equal to v square delta t square times a constant c. Now, this is a very ingenious approximation. If I and I plus 1 have uncorrelated, it's like coin toss. You get ahead, next time there is nothing, you have no correlation. This is exactly coin toss problem, right? Then C is 0. There is no correlation. Just because you got ahead, it doesn't tell you anything what you're going to get next. But turbulence is not like that, it's correlated. So, for turbulence, depending upon your delta t, etc., this C may be 0.5, 0.9. So, there is some correlation between what happened now and what happened to the next time. So, C is a very important parameter. Now, another thing is that this delta t is discretized. So, real turbulence is everything is continuous. So, we want to, he also moved on from discrete problem to a continuous problem by taking number of steps n to infinity and delta t to be 0 and n delta t to be some time t. So, what Taylor did was, hey, I want to go from 0 to time t, but I am going to take infinite number of steps, each of them of infinitesimal time step. So he said that, okay, if the drunkards were moving infinite times and then with small movements, what happens? So he asked this question, and then it turns out that the only thing that you need to know is delta t divided by 1 minus c is something called tau correlation time scale. So one way to think of this is, we are asking this question, delta x at some time and delta x at some time plus a little later tau, how are they correlated? Now, we have passed on from discrete problem to continuous problem, okay? And this looks like, and by the way, I should divide it by delta x t square. So, I normalize it. So, this is the temporal correlation. And this correlation goes down like this. It has a form e to the power minus this time tau divided by tau correlation. This is typically how turbulence happens. In other words, this is a statistical quantity. So, every motion, if it starts moving to the left or to the right, you keep moving in the same direction for tau correlation time. Okay. So, when you do this thing, you can get an expression for this is the equation he derived. So, this is an equation where the problem is drunkard walks left and right with velocity v and takes infinite number of steps for infinitesimal number of times, so that he moves over a time t. And we are asking, if you have millions of drunkards sort of move this motion, what the mean square distance from where they started. Okay, that the, by the way, this x square will be the ball's radius. Okay, so in this case, a bug or a drunkard, where they will be in one dimensional space will be, and it depends only on one important quantity, is tau correlation. So, in other words, if you started moving this way, how long will they continue to move before they move the other way? Okay, that, and in this case the tau correlation has to do with turbulent eddies, how a particle will stay in one eddy and move with that eddy to left or right, etc. So it's a that I'm not saying that tau correlation is easy to get, but at least mathematically that's a very important quantity. If we can't quantify that, it basically talks about if a particle moves in one direction, how long it will keep moving in that direction before it switches and goes the other way. Okay, and that's a very important quantity. Experimentally you could measure, with DNS you could measure, etc. Once you measure that, you have a great handle on what's the ball size, what's the dispersion. The very first slide I showed, how big that ball will be. And if we know that, this is a function of time, right? If I take the derivative of this, it will give you the diffusion coefficient. So in other words, we wanted the diffusion coefficient, which we can stick into a mass balance equation. And where does the diffusion coefficient comes from? We have gone step by step, and we say we now need tau correlation. If we have that, then we are in good shape. So how much correlated a motion is a very important thing. Now the other thing, very important result, when t is much less than tau correlation. In other words, I said that tau correlation is the time over which a motion will remain correlated. Now the answer here is, when you substitute this limit, this is pretty predictable, because the bug or the drunkard is moving at velocity v, and if the time is very short, he hasn't changed this directions at all, so he keeps moving over a time t, and therefore it's perfectly correlated. So this is what happens. Initially this ball will spread, mean square size of that ball will go as this velocity times t. But what happens if the other limit, when you wait a long time, another time larger than the correlation time scale, then also you can get a clean answer. Okay. Now, so in other words, the ball's radius square initially will expand proportional to time, but afterwards will start going little slowly, go as only one a square root of time. So in other words, if you were to draw r square versus time, it will go like this, but then afterwards it will sort of like slow down. Okay. Now where the break off will be, correlation time. So shorter than the correlation time, it will expand more rapidly, but afterwards it will die down. Okay. So what that says is the derivative of this, I told you, time derivative of this is related to diffusion coefficient. So in reality the diffusion coefficient is not constant, not like a it should be a function of time and so on, but that's not what people do, but that's something for us to keep in mind. Okay. So this is called the Taylor theorem. This is called the Taylor theorem. He wrote this in 1922. It's called diffusion by continuous moments. The diffusion coefficient of the particles, so this is the particle diffusion coefficient. In general, it's a tensor. In other words, the ball size doesn't have to be always, it may not be a ball. For example, I will tell you, if you have a pipe and let us say you have turbulent flow, and we do the same experiment, here is a probe and it's releasing particles. It's keep releasing particles. Or one way to think of this is it released a blob of particles. And this is a turbulent pipe flow. So you squirted a little sphere volume of particles, and I ask you, what will the particles be? Where will they be a little later? Now, If the flow had been laminar, it would have come down and it would be like this. I must tell you that even in a laminar flow, particles are jostling against each other and it will spread a little bit. But in a turbulent flow, it will spread both in the streamwise direction and turbulent in the transverse direction, much like the vertical ball being dropped and the big ball that happened. So this is the same phenomenon that I showed earlier. The same thing. Now in a pipe flow, here it was just gravity was pulling. In a pipe flow, it's a non-isotropic problem. Okay, pipe flow turbulence is not isotropic. Streamwise velocity fluctuations, transverse velocity fluctuations are not the same, and therefore, what used to be a spherical ball becomes like an ellipsoid now. And that's why, in other words, streamwise diffusion is not the same as transverse diffusion. And that's why I need to put here diffusion is a tensorial quantity. Okay, if it's isotropic, then this tensor will be diagonal with constant elements. Every direction has the same diffusion. But in general, we must agree that turbulence is not necessarily isotropic. If it's isotropic, then this is diagonal and with constant elements. Otherwise, it will be non-isotropic and whatever it is. And we also saw that this diffusion coefficient is a function of time. So in other words, the true problem, this may not be how we model in Euler-Euler method, but if we use Taylor's ideas, we understand that turbulent diffusion of particles is tensorial and time dependent. Okay? And this, by definition, you can do this experiment in your Euler-Lagrange simulations, or typically Euler-Lagrange simulation. In other words, if you have a pipe flow or fluidized bed, you put a lot of particles. You have to do the experiment that we talked about, is you mark your particles and release it at some point and watch it grow for some time. And you have to repeat it many, many times so that you can collect how much your particle, what's your mean position, what's your displacement from the mean position. Now here I and j are not the particle number. This is I and j go 1, 2, 3, x, y, z positions of the particles. So here we are calculating how far away the particle's position is in the ith direction and the jth direction, and average over all the particles that you have released. Okay. Now if it's isotropic, then this quantity will be diagonal and it will be the I and j, ij not the same will be 0. When I and j are 1, 2 or 3, you will get the same answer. So in other words, the answer will be there, but in general we expect the fact that this may be a tensorial quantity and it's a time dependent quantity and so on and so forth. Okay. Now I am not going to derive this. Taylor derived this, again a brilliant expression. He proved that this is equal to so it is a time integral. So this diffusion coefficient is equal to time integral of a temporal correlation. So what this is time correlation of particle velocity at two different times separated by Z. So, in other words, what this quantity is, let us say you are doing Euler-Lagrange simulation, you keep tracking the particle, you calculate the velocity, ith component of velocity at some time, and jth component of velocity z seconds later. Okay. And this c is a variable. You have to do it 1 second apart, 2 seconds apart, 5 seconds apart. In other words, you have to build a correlation between ith component of particle velocity and the jth component, where I and j go 1, 2, 3 at varying time separations. Okay. So, you can get plots like this, R11 as a function of z as a function, it will be like this. You can build this information from experiments or from simulations, and similarly for R22 and R12. So, in other words, you have 9 components, each of them function of time separation. So, this is the Lagrangian velocity autocorrelation. You take the particle, you follow it, you calculate the velocity. And he proved that this quantity, but this is a normalized quantity. So, it will be 1 when time is separation is 0. Okay, it has been normalized. So, he proved that this diffusion coefficient is related to this in this way. Okay. And why is it important? Because this is how so you can now look at this quantity is a decaying quantity. Okay. So, it goes down. So, you can precisely measure what is your diffusion coefficient and how it is a function of time. So, for large time, for t going to large, when you use so this function of time is not that important, okay, because you see what this says is area under the curve. So, this is simply saying integrate from 0 to t this function. So, this is nothing but the area under the curve, right. Now, if you wait for times longer than this, area under the curve is a constant. So, in other words, diffusion coefficient is a function of time only for short times. If you wait long enough, according to Taylor's theorem, diffusion coefficient becomes constant. Okay. And this is the constant people use in Euler-Euler simulations, as diffusion coefficient is a constant. But if you are using a pipe flow or something, it still remains non-isotropic. Streamwise diffusion may be different from transverse diffusion. Most diffusion models will ignore the time dependence because they will assume that diffusion is long enough. Okay, that is not a problem. But this non-isotropic nature is often neglected, but it is something that you might want. If your problem is isotropic turbulence, then there is not a big problem. Okay. So, that is the last slide of my the day, and I wanted to say that random particle velocity, so randomness in particle motion, which comes from turbulence, results in diffusion or dispersion. Now, this random particle velocity is not just due to ambient turbulence, it can be due to pseudo turbulence. The reason I say this is, imagine that you have a tank and fluid is stationary, no other turbulence, and you throw in a bucket of sand in there. When they are all settling, each will be making the other guy's velocity a little bit like random walk problem, right. Therefore, this is what I said, you take a handful of sand and you put it in there and you release it. So, you have released a ball of sand, there is no other turbulence. The turbulence is created by the particles themselves due to pseudo turbulence. Wouldn't you expect that ball to fall down but get bigger and bigger and bigger and bigger. So this is an issue with dredging. People do see these things. Okay, so they release, and then where does it go and settle down is a very important question. And that dispersal is due to turbulence, and that turbulence is due to particles themselves. So pseudo turbulence create the dispersal of the particles. Okay. Now mean square displacement is related to two-time particle velocity correlation. This is the RIJ I was talking about. Okay. So two-time particle velocity correlation is a very important quantity in explaining the effect of turbulence on dispersal. And the last thing I want to say is that, having said all these things, that two-time velocity is not an easy quantity either to measure, or in simulations it's not that difficult, but experimentally it's a hard quantity to measure, and it's a hard quantity to model, and there's a lot of work people have done in trying to come up with some good models for Rij, because once you integrate this you get directly the diffusion coefficient. Okay. With that, any questions on that? So I've tried to give various flavors of how turbulence and particles can create turbulence, and can modify particles and their dispersal, etc. Okay. Yes.
So regarding Rij, so it's a tensorial quantity because of it can move in any direction, the particle velocity.
Yes. So Rij, as I said exactly, is correlation between, if you take R11 and let's say let's take it to be vertical direction. R11 is vertical velocity of the particle now and vertical velocity of the particle tau seconds later. R12, 1 is down and 2 is horizontal. Vertical velocity of the particle now and the horizontal velocity of the particle at a later time. That could be 0 because it may move left or right. So some of these quantities. But what about R22? Is the horizontal velocity of the particle at time 0 correlated with the horizontal velocity of the particle at a later time? So you need to find all 9 such combinations.
So would we say that the diagonal elements are more important?
Absolutely, absolutely. So off diagonal terms will very likely be 0. So the diagonal terms are the important one. But for the settling problem, you can clearly see if 1 is down, 2 and 3 are horizontal. So this term, let's say call it A, you will get this kind of a form. The 2 horizontal directions are the same, but the vertical direction it could be spreading faster because it's a very preferred direction. Things are falling down, and as you mentioned, the cross terms could all be 0 statistically, because a falling particle, why should it go to the left or to the right or to the front or the back? They all look the same. So by symmetry you may argue, and you may say that only the diagonal terms are important, and in this case of a vertical settling problem, vertical direction is different from, but the horizontal direction is going to be same. Same way in a pipe, streamwise direction may be very different from transverse direction. Okay.